Before I begin, let me fix erratum. So, in the theorem on the wave equation, I wrote the conservation of energy d by dt u dot t square 0 omega plus mod u dot t square 0 omega equals mod g square 0 omega plus mod f square 1 omega. So, the correction is that this should be 1 omega, because the space is for du by dt it is in L2 and this in H10, and this should u corresponds to f and du by dt corresponds to g, and that is conserved. So, this is the thing. Another place, when writing the equation for Rn, I wrote d2u by dt, you would have figured it out, it should be actually d2u by dt square. Okay, so that. So, today we will look at one more example. So, this is the Schrodinger equation. So, this is an equation which is important in quantum mechanics. So, you take omega contained in Rn, bounded open set, and gamma equals d omega. We look for u from 0 cross omega cross 0 infinity, taking values in C. For the first time we are going to deal with something which is complex valued, well, for few moments, and such that I du by dt minus Laplacian u equal to 0 in omega cross 0 infinity, u equal to 0 on gamma cross 0 infinity, and u of x 0 equals u0 x for x in omega. Okay, so you have an I here in front, otherwise it looks very much like the heat equation. So we are want to deal with real functions. So we write u equals u1 plus I times u2, the real and imaginary parts. So we separate the real and imaginary parts in this equation, and then so separating real and imaginary parts, we get the following system of equations: du1 by dt minus delta u2 equal to 0 in omega cross 0 infinity, du2 by dt plus delta u1 equal to 0 in omega cross 0 infinity, u1 equal to u2 equal to 0 on gamma cross 0 infinity, u1 of x0 equals u10 of x, which is the real part of u0, and then u2 of x0 equals u20 of x. This is x in omega. So, u0 equals u10 plus u20, okay, I times u20. Okay, so this is the real and imaginary parts. Okay, so we have a following this system of equations which we want to solve, and now we have the following theorem: omega in Rn, bounded open set of class C2, u10 and u20 in H2 of omega intersection H1 0 of omega, then there exists a unique solution of star such that, okay, so integral on omega mod u1 xt square dx plus integral on omega mod u2 xt square dx equals integral mod u1 0 square dx on omega plus mod u2 0 square dx. Okay. So, this is for all t greater than 0. Okay. So, this is the theorem which we have. Okay. So, proof. So, we take V equals L2 omega square and A dA contained in V to be defined by d of A equals H2 omega intersection H1 0 of omega square and AU equals delta U2 comma minus delta U1. So U is U1 U2. Okay, so you have delta U2, delta U1 in D of A. Okay, so this is the thing. Then star implies that U dash T equals A of ut. So du1 by dt, du2 by dt, that is u dash t minus delta u2 plus delta u1, and so that is equal to delta u1 delta u2 minus delta u1 when you take it to the other side, and therefore that will give you precisely d2u by du. Okay. T greater than 0 and u of 0 equals u0 equals u1 0 u2 0. Okay. So, if u belongs to D of A, then you have AUU which is equal to integral omega delta u2 u1 dx minus integral on omega delta u1 u2 dx, and u1 u2 are in H2 intersection H1 0, and that is equal to minus grad u2 grad u1 dx plus integral grad u1 grad u2 dx dot product, and that is equal to 0. So, AUU equal to 0. Now, if you go back to the Galerkin method example, this implies, if you go and look at that, it precisely says range of I minus A equal to B. Okay. And same method will imply range of I plus A is also equal to B. Therefore, A and minus A are both. So, you just go to the previous chapter where I gave you an example of the Galerkin method. I mentioned that that will be useful in the solution of Schrodinger equation, and that is exactly, if you look at right range of I minus A equal to B, that is exactly what we proved. There exists a unique solution to that. We did not use the Lax-Milgram lemma, we used the Galerkin method instead. Okay, so A and minus A are both maximal dissipative, implies they together generate a group of isometries. And this implies conclusions of the theorem. So, if u0 is in the domain, which it is, which we are given, u0 is in the domain. So, u0 u1 0 and u2 0 are both in H2 intersection H1 0. So, u0 is in the domain, and then you have, and this is the condition which says that it is an isometry. It preserves the norm of the initial value throughout the thing. Okay, so this represents the solution. So therefore, you have a unique solution for the Schrodinger equation by through its real and imaginary parts. So the Schrodinger equation looks like the heat equation, but it solves used methods like the wave equation here. Okay, and if omega equal to Rn, then you have I du by dt minus Laplacian u equal to 0 in Rn cross 0 infinity, and u of x 0 equals u 0 of x, okay, x in Rn. There are no boundary terms now. So then you can write as using the Fourier transform, you can then show that u of x t is equal to exactly as in the calculation which we did in the Fourier transform. You get minus 4 pi I t power minus n by 2, because instead of I du by dt we have I du by dt, that is the only thing. So wherever t comes you will have an I t there, okay, and integral over Rn of e power minus I mod x minus y square by 4t u0y dy. Okay, so this is the solution of the Schrodinger equation in Rn, and again you will have that u of x in L2 norm will be preserved. Okay, so this is about the Schrodinger equation, and we will, so that brings us to the end of the examples which I wanted to talk about.